What's up, guys? So today we'll be doing a Doppler effect. It's a very short topic and it's a paper one topic, and it consists of plus minus 18 marks. So it's a very short topic, as you can see by the marks. So what's Doppler effect, right? So Doppler effect, it's the apparent change in frequency of sound detected by the listener as the source of sound, and the listener are moving relative to each other, right? So that's the definition of Doppler effect. It's the apparent change in frequency, right? Underlying frequency of sound, right? Detected by the listener as the source of sound. I forgot the source of sound, and the listener are moving relative to each other, right? So we all know that sound is a form of a wave, right? But then what kind of wave is sound? Sound is a longitudinal wave, right? And we know that longitudinal waves consist of compressions and also reflections, right? So there is an audible range that we will be looking at when working with Doppler effect, right? So we all know that frequency is measured in hertz, right? So there is a range for frequency whereby the human ear can hear, and there is a range where the human ear cannot hear, right? So the audible range is just something, it's not tested in the exams. So the audible range for the human ear, it's between 20 hertz to 20 kilohertz. 20 kilohertz. That's the audible range for a human, right? So anything that's, if the frequency, if f is less than 20 hertz, right, we call that infrasonic sound, right? And then if my frequency is greater than 20 kilohertz, we call that ultrasonic sound, right? So ultrasonic sound is basically something that can rupture your eardrum. It can cause you to lose your hearing ability because its frequency is way too high for the human ear to handle. But then infrasonic sound, it's sound that you cannot even detect. It's so faint that the human ear cannot pick up infrasonic sound, right? So that's just what Doppler effect is about. Doppler effect is all about sound and its frequency, right? But then we've got a condition for Doppler effect to be observed, right? So we've got a condition for Doppler effect to be observed. Right? So the condition for Doppler effect to be observed is that they should be moving relative to each other as stated in the definition, right? So what we mean by relative motion is that when the listener is stationary, the source of sound should not be stationary, or you can rather say the source of sound should be moving, right? So relative motion, it's just saying that the source of sound and the listener cannot both be stationary. One has to move while the other is stationary. You understand? That's what relative motion means. So in order for Doppler effect to be observed, we need to have relative motion, where if the listener is standing still, the source of sound is moving. If the source of sound is standing still, the listener is moving. So that's the condition that is required for Doppler effect to be observed. So I'm just gonna draw a small diagram here to illustrate what is happening, what Doppler effect actually is in real life. So let's just say this is the source of sound, right? And this are my waves. Let me make them, because I want them to be in a certain way for you to see what I actually mean. I think that will do, right? And then we've got two people this side, one person this side, and then we've got the other one this side. And then the blue dot is my source of sound. So maybe let's just say it's a car or anything. As long as it can produce sound, it can be my source of sound, right? So the wavelength of the source of sound. So let's try and analyze this diagram and what it actually means, right? But then before analyzing the diagram, I want you to remember one thing. I want you to remember that frequency is inversely proportional to wavelength, right? So in order for you to understand what's going to be going on, frequency is inversely proportional to what? To wavelength. So these blue lines, right? These blue lines represent my wave, right? So if these blue lines represent my waves, right? Obviously this, the distance between my concentric, they're not really concentric circles, but then you can see what I mean. The difference between, not the difference, the distance actually between this circle, this oval shape, and this oval shape is gonna form my wavelength, right? Meaning this is also my wavelength, this is also my wavelength, and this is also my wavelength, right? And remember, the source of sound has its own frequency, which we are going to denote by Fs, which represents the source of sound. Mic also is going to register a certain frequency from the what? The source of sound. Because Mike is a human. He obviously has ears, right? And he is able to hear the sound emitted by my source of sound, which in this case we said it's a car, right? But then looking at this, my wavelength is much larger on the side of Tim compared to the side of Mike, right? And if my wavelength is larger, that means Tim's frequency, the frequency of the listener, right, is going to be less compared to the frequency of the source. The reason Tim does not have a frequency greater than the source is because obviously the source of sound is moving away from Tim. It's just like a car. If you're standing next to a car, right, and the car is playing music, but then the moment the car starts moving away from you bit by bit by bit, you start hearing less of the sound. The sound starts to fade as the car gets further and further away from you. That's what's happening from Tim. So as the source of sound is moving further and further away from Tim, Tim is going to register a frequency less than the frequency emitted by the source of sound, right? So we also look at mic, right? So we can see that the wavelength on mic side is a bit shorter. And because wavelength is decreasing as the source of sound gets near and near mic, we say that mic, the frequency of the listener, which is mic in this case, is going to be greater than the frequency of the source. I hope you understand that, right? So this entire thing, right, it's just illustrating the how the frequency and the wavelength are kind of related, and how Doppler effect is observed, right? And remember, I said in order for Doppler effect to be observed, right, the source of sound has to be either moving while the two listeners, which is mic and team in this case, have to be stationary, or mic and team have to be moving while the source of sound is what is stationary, right? So from this, right, we know that sound travels through air, obviously, right? So meaning that sound is going to have a certain speed that it travels through air, right? So the speed of sound in air, right, is 340 meters per second, right? But it is not fixed. It's not always the case that the speed of sound in air is always going to be 340 meters. It can change depending on various factors, right? So one thing that can change the speed of sound in air can be something like the air resistance. You understand? Let's say someday, today is a windy day. Obviously, when it's windy, it's hard for me to hear somebody in the wind, because have you ever tried to speak to somebody while it's windy? You see, it's kind of hard for you to hear them because the wind, right, it's affecting the speed at which the sound reaches your ear. You understand? So those are the things that can affect the speed of sound in air, right? But then if the examiner, right, does not say anything about the speed of sound in air, we assume that it's 340 meters per second. But then if the examiner gives us the speed of sound in air, we use the given speed, right? So the formula to calculate the frequency of the listener, right? So right now we are gonna come up with a formula that's gonna help us calculate the frequency of mic, the frequency of the frequency which mic detects as the source of sound is moving towards him, as the car is moving towards mic. And we are gonna try and calculate the frequency of sound detected by Tim as the source of sound is moving away from him, right? So the formula for Doppler effect, it's the frequency of the listener is equals to the velocity plus minus the velocity of the listener over velocity plus minus velocity of the sound multiplied by frequency of the source, right? So the reason it's plus minus is because it depends on whether the scenario is moving towards or on whether the scenario is moving away from, right? Or it's moving further and further away from the listener, right? So let me just so F at L, we say it's the frequency of the listener, frequency of listener, right? F at S is the frequency of the source of sound, right? And remember that frequency is measured in hertz, okay? My V is the speed of sound in air. which is measured in meters per second. And then if not given the speed of sound in air, we assume that it's 340 meters per second, right? My VL, it's the speed of the listener, right? So the speed of the listener, you're going to be given the speed of the listener in the question. It's also measured in meters per second. And then we also have my VS, which is the speed of the source of sound, right? So these are all my variables in the formula, right? So in the next video, I will be explaining how each formula, how each variable in the equation, in the Doppler equation, is affected as the source of sound approaches and also as the source of sound moves away.